Good evening. If people can please sort of find their seats. First of all, my name is Brian Weiner. I'm the chair of the physics department here at Ohio State. And on behalf of our department, the College of Arts and Sciences and the university, I want to welcome you to the 57th Alpheus Smith Lecture. This is a lecture that we hold annually, and it's intended to bring distinguished scientists to Ohio State to present insights on subjects of scientific interest to the campus community. The lecture is named for Alpheus Smith. It's a tribute to his memory, and it was made possible by donations from his family and friends. And if this is your first time with us, I just want to give you a little bit of background on Alpheus Smith and who he was. He was a physics professor he started here in 1909. So over a century ago. He became chairman of the physics department in 1927. In 1938, he became dean of the graduate school. He tried to retire in 1946, but was immediately roped into being president of the OSU Research Foundation, which was just starting at the time, and he served in that capacity until 1958. So he served the university for almost 50 years, and this lecture is a recognition of that service. And it was first held in 1960, well over 50 years ago. I want to talk to you a little bit about the speaker we have tonight. So tonight's speaker is Professor Stephen Chu. He is the William R. Kennan Jr. Professor of Physics and Professor of Molecular and Cellular Physiology at Stanford University. He received his undergraduate degrees in mathematics and physics from the University of Rochester, and then he went on to University of California, Berkeley, to get his PhD in physics. He headed up the Quantum Electronics Research Department at AT&T Bell Laboratories, where he did his work on laser cooling and atom trapping that led to him being named a co-recipient of the 1997 Nobel Prize in Physics. He went on to serve as director of Lawrence Berkeley National Laboratory, where he was active in the pursuits of alternative and renewable energy technologies. And then in 2009, he was tapped to be the 12th U.S. Secretary of Energy, and he served in that position until 2013. He was the first scientist to hold a cabinet position ever, and he was the longest-serving energy secretary. He's received numerous honors for his scholarly achievements, including being named as a member of the National Academy and the American Academy of Arts and Sciences, and he is actually also currently the president of the American Association for the Advancement of Science. So tonight, Professor Chu will be speaking on the climate challenge and paths to a more sustainable future, so please join me in welcoming Dr. Chu.
So, thank you very much. It's a pleasure to be here and to talk about something I care about. But just so you don't get the wrong impression, I was an unwilling, drafty bureaucrat, both as director of Lawrence Berkeley Lab, but also as Secretary of Energy. I never wanted to be a bureaucrat, but I was willing to do it. And I was asked, in case you're wondering, why 4 years, why not 8 years? And that was not my choice. My wife decided 4 years was enough. And so compromise was 4 1/3 years. She wanted to go back to California, to Stanford. Okay, so what I'm going to talk about today is something very near and dear to my heart, and it has to do with the climate challenge. I know many of you, or most of you in this audience, know about this issue, but I want to tell you perhaps a few things you may not know about and where we're heading. But I hope to devote the majority of the time to talk to you about the science and technology changes that can make much better choices. Ultimately, we need to develop technologies so that cleaner energy is more affordable than fossil fuel energy, period, without subsidy. And I feel pretty strongly about that. All right, so let's review a little bit about what happens in the recent history. The recent history, I'll start with 1 AD. It's arbitrary time, but this is the carbon dioxide level global average in the world. And it was pretty stable until very recently. And we're now at a 410 parts per million when you seasonally average. All right, so the question is, the climate has changed dramatically in the past, and in those changes, temperature and CO2 have more or less tracked each other. So what is different about this? And so there are two things that are different. One thing that's different is if you look at the estimates of how much greenhouse gases have been emitted by humans and divide by 2, because half of it gets reabsorbed by land and plant life and ocean very quickly with a time constant less than 10 years, 5 years. It quantitatively agrees with global carbon emissions, so it's just bookkeeping, it's arithmetic. But you need to divide by 2 because the land and oceans pick up that. Okay, but there's a much more significant thing because as I said, temperature has risen in the past, going back tens of millions of years. Good records based on glacial stuff over the last 800,000 years. So there's something else that you may or may not know about, and that has to do with the ratio of carbon-14 to carbon-12. Let me remind you where carbon-14 comes from. It's made in the upper atmosphere due to proton bombardment that creates neutrons that then convert nitrogen into carbon-14. Carbon-14 is radioactive. It slowly diffuses down into the biosphere, into everything. And you and I have carbon-14 in our bodies. And carbon-14 for short-term radioactive dating is the tool of choice. Because if, for example, you were a plant and you were embedded in carbon-14 and you turn this plant into cloth, like the Shroud of Turin, it's no longer connected, and you can radioactively date whether the Shroud of Turin was actually in the time at 2,000 years ago. So what's the deal? Carbon-14 has a lifetime of 5,700 years. And if you look at the carbon-14 to carbon-12 ratio, it's being diluted. Now, carbon-14, as I said, it mixes in the atmosphere, and you and I have it. Suppose it's been rumored we will all eventually die. I'm trying to resist this rumor. But suppose we do die and we're put away in a pretty good coffin and we're sealed from the environment for 3 or 4 or 5 carbon-14 lifetimes, and we exhume you and I, and we put you in a fossil fuel plant and we burn you. You have no more carbon-14 in you. So what you add is carbon-12 and a little bit more nitrogen. That's it. Okay? So that agrees quantitatively with fossil fuel emissions. So that means the carbon-12 to carbon-14 to 12 ratio has been diluted, agrees quantitatively with carbon that had to have been sequestered tens of or hundreds of times longer than a natural tree lifetime / decay and most ocean carbon cycles. So fossil fuel is the culprit. It's been sequestered. And that also agrees quantitatively. So this is kind of the smoking gun footprint that most scientists who pay attention to this recognize. It's not like previous carbon temperature CO2 cycles. All right, so let's look at some of the effects. Are glaciers melting? Is the sea level rising? There's a short answer. The answer is yes. You can take anecdotal evidence. This is Muir Glacier in Alaska, August 1941, August 2004. It looks kind of different. But this you can say is anecdotal evidence because there's a few glaciers that have increased in size. And so it turns out we have much better data based on satellites, both gravitational changes and also high-resolution down-looking radars. And this is a time-lapse photograph of the glacial melt in Antarctica. As you see that little dot working across as a function of time. Those black, green, blue, red things are different satellite missions. And the time scale is 1900. Nothing really happens until about 2005. And after 2005, Antarctica is melting. Greenland is melting much more significantly. And it turns out that the melting of Greenland and the Arctic ice sheet melting is intimately coupled with Antarctica melting. The water that flows back from the Gulf Stream back down in a conveyor belt goes all the way back to Antarctica. The warm water, it's warmer water, it melts back the grounding line of glaciers that go into the sea in Antarctica, so the friction is decreased, and so the glaciers are sliding off the continent faster. And so this was not fully appreciated until the last 10 or 15 years, that it's linked and it's melting fast, and how fast is fast. In both Greenland and Antarctica, the rapid moving glaciers are moving out at 1 kilometer per year. So it's a redefining glacial speed. There's another data point that's not a climate model, but it's a matter of history. In the last warm period, the last interglacial ice period, we were about 1.5 degrees warmer than we are today. We know what the sea level was during that warm period based on fossil evidence of critters that lived in the boundary between land and ocean. You can be radioactively dated, and you have to average all around the world because land rises and falls locally. And so the measurements of what it was 1 degree, 1.5, 1/4 degrees warmer than we are today is the sea level 6 to 9 meters higher than today. So that's the UN target, by the way. Stay within 1 degree of today. But we thought that that level would take a couple thousand years. And now all bets are off. The sea level is not going to rise this century. It'll probably be less than 1 meter. Next century, probably 2 or 3 or 4 meters. And so it's now been accelerated from millennia to a century or two. Again, this is within the last 5 or 10 years. That the climate is much more sensitive, the glaciers are much more sensitive than we thought. All right, so let's look at basic scenarios. Now, I've so far avoided climate models. There's lots of uncertainty in climate models. And climate models mean that you have to make projections about what the CO2 is, and of course that also depends on what the world does with emissions. It also depends, we pretty much understand the ocean and land uptake, so that's now not as big a deal. But still, it requires models and it requires projections. And so these are some of the projections of what the climate models may look like. These are detailed scenarios, but it doesn't really matter. As a physicist says, forget about the detailed scenarios. Let's take this. What would happen if we're there? So it's the blue line, the lower blue line is how do you stay below 1.5 degrees, 2 degrees for sure. And the green line is other scenarios. The y-axis is total greenhouse gas equivalent CO2 emissions, which also includes methane and all the others folded in. And the 0 means the entire world has to go negative in carbon emissions by 2070 or 2080 from everything, if you want to achieve 1.5 to 2 degrees. The entire world, not just electricity, but transportation, process, heat to make steel, cement, agriculture, everything has to go negative. Okay? We're not going to do that. And so, as I said, the high-end projections are it could be a couple meters by 2100, but again, it's remains to be seen. Okay, so what are some of the other consequences that people already feel in the United States and around the world? The summers are hotter, and so you need more irrigation when you needed irrigation before. When you didn't have irrigation, you now need irrigation. And the water aquifers in the Midwest are being depleted. They're being depleted due to a lot of reasons, but it's basically the rainfall patterns have changed, and the slow trickle from the Rocky Mountains is no longer what it's going to be, and so there's issues there. India, China, the Andes, they're all seeing water depletion shortages. So we see increased droughts, heat waves. In California, we've had such serious forest fires in the last several years that the main utility company in Northern California, Pacific Gas and Electric, has now instituted a couple of blackouts as precautionary measures because the forests are so hot and dry that they've actually blacked out 1 million people. Turned off the electricity for days. They shut down UC Berkeley for 3 days because of the forest fire threats. Okay, so this is real stuff that's happening. And I think, to me, the sea level rise is not going to be the first thing that really hits home in the world. I think it's going to be water supplies and collapsed agricultures. This is a map of where the water-stressed areas are in the world. California lights up a lot. And so it's these water-stressed areas. If the Himalayan plateau, the Rocky Mountains, the Sierra Nevadas have spring rains instead of spring snows, the glacial melts instead of the slow trickle will become floods. And this is not rocket science. And so this is something that's has me very worried. If you think 5 million refugees going to Europe was a problem, move the decimal point over by 1 or 2 places. Because as fragile economies collapse, this could happen. Okay, so let's look at where we are. This is 1750 to 2000 and I think 15 or 16. On the y-axis is plotted cumulative carbon emissions. Very important that we think of cumulative emissions. As I said before, half the carbon dioxide gets rapidly absorbed by the oceans. The inorganic carbon gets into the biocarbon cycle. Trees, plants absorb it very quickly. The rest of it's just cycles between land, ocean, and the atmosphere. And that lifetime is estimated. We don't know for sure, but the lifetime of the other half of the CO2 emissions is expected to circulate for about 10,000 years. I don't want to debate 5,000, 10,000, 15,000. So don't think of 2100 as what will happen. Think 21000. Okay, just let that sink in. That you're off by a decimal place. And so that's of concern. If we stay on our current carbon emission in the world, we will go through that red line, which is the 2-degree target of the UN, which includes climate models, in 30 or 40 years, about 35 years, okay? So then you ask, what's the probability of staying below that line? And I'll give you 50 to 1 odds we go past it. The other thing, or 100 to 1. The other thing is that 3/4 of the greenhouse gas emissions occurred in the last 65 years. You think we talk about beginning of the Industrial Revolution, but it's only since about 1950 that it's and it's accelerating. Now, there's a quote ascribed to a Chinese philosopher, founder of Taoism. I couldn't get verification of this. I wasn't alive during that time, but it's something Yogi Berra could have said. If you don't change direction, you will end up where you're heading. Okay? And we're heading past that line by a lot. All right. So that's the bad news, but what can we do about it? We will go through that line. But okay, so let's talk about science, technology, solutions. So before I talk about clean energy, cheaper energy solutions, I want to talk a little bit about energy efficiency. And I'm only going to give you one example. California is leading the United States in energy efficiency in buildings, many, many things. the electrical usage per person in California has remained flat since about 1975 due to forward-leaning policies and the cost of electricity, the bills, not the rates. The rates went up, but the cost to the average household remained the same since for 35 years. All right, but I'm going to tell you about something else and about appliance standards, and it's a good news story. And it had to do, when I was Secretary of Energy, I was publishing papers because my graduate students and postdocs had defined jobs, and so at nights and weekends I would work on papers. I could give up all the other hobbies. I'd stop watching movies with my wife. I'd stop watching movies in airplanes. I would work all the time for the first 70 hours unless there was an emergency, and the next 20 hours I would do science. And but I also did a few things, and this was essentially written while I was Secretary of Energy. And what we're doing is we're looking at the cost of appliances. The blue line is the cost of ownership of the appliance, which is the purchase price plus the cost of the electricity. The little arrows were appliance standards. And starting in California in the mid-70s, California started to introduce appliance standards because refrigerators, for example, were a big, big energy sink. And the dotted lines are California standards and then adopted federal standards. And so not surprisingly for refrigerators, room, central air conditioning, clothes washers, the cost of ownership went down because if you included energy cost. And it's mandated in any efficiency standard that the Department of Energy writes down, it has to reduce cost, period. You have to demonstrate it reduces cost. So that wasn't surprising. What was surprising is the purchase price. It was expected the purchase price would go up. We did this in Europe, we did this in the US, these are US prices, and you see in refrigerators, there was a little bump up in the first, yeah, and then it went down again, and there's little wrinkles if you stare hard at the data. Room and central air conditioning, there were these little plateau bumps if you stare hard at the data, but the trend is not. So what you're plotting on the x-axis is how many deployed shipments there were, and on the y-axis is price, and it's both logarithm. This is a very deep thing. It's not a deep physical principle, but it's called experience curve. You plot on the y-axis cost and logarithm, and you plot on the x-axis how many deliveries you've made. The experience of manufacturing more in quantity makes it go down in a straight line logarithmically, which means it goes down exponentially, a slow exponential. And this is amazingly true for many, many technologies, from automobiles to refrigerators and central air conditioning. But the surprise was the price of appliances went down when you required them to be more energy efficient. And this makes no sense, because it certainly would cost more, and the Department of Energy expected it would cost more. So what was going on? We don't know. This was an experimental data, but I can theorize that if you start with a blank sheet of paper, you could actually make a better thing. And for example, in refrigerators and air conditioners, you make a smaller compressor. Now, having said that, the downside is the appliance makers also made a compressor that breaks sooner. But that was design obsolescence, so I don't confuse it with energy efficiency. We used to have refrigerators that lasted 30 years, and now they last 7. They last 7.2 years when the warranty is over in 7. The engineering is remarkable. And so in any case, it's just data. So we were very proud of this. We submitted to Science Magazine. It went out for review, and we got back 3 reviews. And if I had to paraphrase the reviews, it was something like, oh, by the way, all these people were kind of physicists. They were ex-physicists, except me. I'm still a card-carrying physicist. And the thing was, it doesn't matter what this data says and what these people say. There were economists who reviewed it. We don't believe it. So I said to myself, oh, economists are different than scientists. Okay? Okay, so that was, now, The refrigerator costs declined by 28% for each doubling of production. And if you extrapolate that energy line for more refrigerators, what happens is it's the equivalent of 31 gigawatt reactors working 24/7, or, to drive it home, all the coal plants in Ohio in carbon emissions, just from refrigerator efficiency. Just refrigerator efficiency. It was a few percent of the electricity budget. Okay. So it was a big deal. And it saved the consumers money. Now, many people don't like regulations. There's regulations about low flush toilets, and the first ones didn't work so well. But I put a new toilet in my home that's 1.25 gallons instead of the California's 1.6, and it works much better. It works better than the 2.5-gallon ones. They just had to engineer it. So the first things may have little bumps and wiggles, but and the shower heads also. So here's a quiz. I'm a professor, so I'm going to give you guys a quiz. How many free market economists does it take to change the light bulb? Okay, now there's not clickers, so I'll give you the answer. And the answer is none. If the light bulb needed changing, the free market would have done it. And that was the review from The Economist. There's no way in the world you would design something more expensive and less energy efficient. The free market would have done it. But it doesn't do it. It doesn't do international fishing well. It doesn't do a lot of things well. So anyway. Okay. So energy efficiency is a big deal, and it's better than free. Now, if you really want to look at what are the bad actors in climate change, you have to look at the sources. So this is a plot from the IPCC's Physical Basis of Climate Change 2013, and it looks at the CO2 fossil fuel and industrial processes. That's the orange line. It looks at, you see this? Okay, it looks at CO2 forestry, agriculture, from just forestry and agriculture. It looks at methane. Methane, the majority of methane comes from farming and animal raising, not from the oil and gas industry. Virtually all the N2O comes from fertilizer runoff, and then there's a little bit else. And it turns out that agriculture is half the habitable land. That means you take away the oceans, you take away the mountains, the lakes, and you find that half of the habitable land in the world is under agricultural production or grazing. And so it's a resource, and so as the world population grows, what are we going to do about this? So forestry agriculture is more CO2 greenhouse gas emissions than all electricity generation in the world. Okay? So let's move on. So let me tell you a little bit about agriculture. This is another quiz. Can you spot the native corn from the original wild corn? This is the wild corn. They're different. Okay, here's another thing. If you look at the biomass in the world, the distribution of biomass, it turns out most of the biomass is not surprisingly in plants. Bacteria is second. There's a big uncertainty. It could be even factor 2 uncertainty because bacteria we don't see. And that little itty bitty thing at the bottom end, this little thing, are called animals. So let's expand on animals. And it turns out arthropods are the dominant biomass of animals. What are arthropods? They're spiders, insects, millipedes, crustaceans. Fish are second. They're not first. And let me look at this. Mammals. They're wild mammals, livestock, and humans. Livestock and human biomass is 96% of all biomass in the world. All the lions and tigers and bears and mice and rats and deer are 4%. So us plus the animals we eat is the overwhelming majority of biomass. I'm just trying to impress upon you how much we've geoengineered the world. We've geoengineered animals too. This is American animals. The full circle is the natural lifetime of beef, cattle, pigs, and broiler chickens. Chicken you buy it in the supermarkets, only alive since hatching for 40 days. Pigs, 22 to 26 weeks. Cattle, a year and a half to 2 years before they're slaughtered. The pigs are slaughtered in this very short time, and they weigh 280 pounds. And so the livestock have been bred to grow very efficiently on much less food. And in fact, it's kind of astounding because some of the breeding has actually profoundly changed the livestock. Domestic turkeys are only alive for an average of 3.5 months before they're a 14-pound turkey in Safeway. The big toms, 25 pounds or longer, but they're a little bit weird because they're so breast heavy that they can't mate, so they're artificially inseminated. Okay? And they look different. This is a wild turkey. Don't know how old they are, but I can guarantee you they're not 3.5 months. I can tell you with some certainty what the age of some wild turkey is. Wild turkey 101 is 8 years old, so they say. Most of the big fish in the oceans have been depleted, and so the global wild salmon catch in metric tons from 1950 to 2010 has shrunk dramatically, and those green curves on the right-hand side are farm-raised salmon of various breeds. Atlantic salmon grows faster than West Coast salmon, and there are farm fisheries of Atlantic salmon. There was a discussion in the postdocs. It turned out that the Atlantic salmon that would have grow faster than the West Coast salmon leaked out because they're raised in pens, and they leaked out and they started competing with the much more valuable wild salmon. And so that's an issue. There is a new type of salmon that has just been put on the market in 2019 that's genetically modified from the fast-growing salmon. They only did 2 genes from fast-growing salmon, and they do what's called a promoter. So the gene for the growth and the promoter means the salmon get to grow all year round. And so in the same amount of time, for a very short period of time, and you get these salmon, and the difference is profound. Okay, so salmon, first farm. Now these salmon are not allowed to be in the ocean or rivers or lakes. They have to be on land with heavily filtered water so they don't pollute the wild salmon. It took the FDA 20 years, and there were all sorts of protests about having genetically modified salmon because there were even bad things that happened with farm-raised salmon. If improperly raised, they're doing all sorts of things to the ocean. So, but again, it's agriculture and aquaculture. This is the carbon emissions around the world. The red is China. China leads the world in carbon emissions today, followed by the United States in this turquoise color. The EU 28, that includes Great Britain, is in the yellow on the bottom. If dairy cows and cattle were a country, they would be ahead of the EU in greenhouse gas emissions. Okay, let's just sink that in. And so it's because of, you're raising grains and things. Grazing cattle are worse. It's much worse for the climate, it turns out, than high-intensive farming and feed pens, which have other problems. So, and so it's 4.6 gigatons of CO2 from beef and cattle. So, what is happening? So there are a few entrepreneurs who decided to try to make hamburger meat, because of the beef, the lion's share goes into hamburger meat, taste as good or better than ground hamburger meat. The founder of Impossible Foods Burger was a very distinguished biochemist at Stanford, a Howard Hughes Senior Medical Investigator, member of the National Academy. He calls me and says, Steve, you'll be proud of me. I quit my job at Stanford, and I'm going to do something about climate change. I'm following your example. I said, you did what? And he said, no. I decided what I can do. I know biochemistry, so I'm going to figure out how to do biochemistry to make soy and other proteins and pea proteins really taste like hamburger meat. And it includes that he experimented with several types of hemoglobin-like molecules, beef hemoglobin, soy hemoglobin, and he found that the soy hemoglobin is actually pretty good, except they couldn't extract it efficiently from a soy root plant, so they stuck it into yeast, and they're genetically having the yeast grow hemoglobin. So it's the blood taste. You like the blood taste. I did not ask him whether he did blind tasting with human hemoglobin. It's a little creepy. But it turns out that the soy hemoglobin won out above the beef hemoglobin, and it has a longer shelf life. So remarkably, it's sort of, how many people here have tried almond milk? Oh, lots. It stays fresh in the refrigerator a lot longer than milk. It's the same issue. For whatever reason, the animal stuff rots faster. Okay, if you want to make your normal milk last longer, you have to put your refrigerator down to the minimum, which is like 34, 33 degrees, just above freezing. And you can get meat staying in your refrigerator. It stays nice for a week. Milk stays for over a week. I have a constant fight with my wife, but she looks at expiration dates and freaks out. And I've got aspirin that's expired 4 years ago, and I can guarantee you it works just the same. Anyway, never mind, I digress. But so now there's, at least in Palo Alto, you know, like 5 or 6 companies selling this stuff. And Beyond Beef tastes pretty good. Impossible Food, it's impossible to buy it in a supermarket. You can get it in McDonald's and whatever, but they have to gear up production. There are some other versions that are really terrible. So I'm patiently going through this. My wife has to put up with this. And if I were a meat producer, I would put out really crappy stuff. Because you want to poison the market. But these are not bad. Now, another hint, cook them medium rare. They don't taste good when they're well done, brown in the middle, but neither is hamburger. But okay. So there are meat substitutes. But you can go further than that. There are innovative companies that are looking at annual grains. Corn is a heavy fertilizer. Heavy fertilizer means heavy energy inputs. And we know that certain plants like legumes actually work up symbiotic relationships with the microbes in the soil. So the microbes feed the plants nitrogen from the air. And Pivot Bio is a startup company in the Bay Area. So they're breeding microbes, and little changes in the corn, but it's mostly in the microbes. They put the microbes on the seed, and they sell it, and it greatly reduces the need for nitrogen fertilizer. Phosphate is next, but nitrogen is way down. What's good about it is the corn likes it better because the corn sends these chemical signals to the microbe and say, I'm hungry, feed me some nitrogen stuff, and they respond. And so on the right-hand side is a field test of this. It's now just entered into commercial deployment, and the right-hand side is sort of standard corn, which has an issue. So the issue really is it going to make farms more productive, and it's going to be cost benefit to the farmers? And the hope is the answer is yes. So because you don't regulate farmers. Farmers do not want to be told what to plant. And so it's going to be purely economic, and so there's hope. So there's stuff like this going on. Now, the good news, I'm not going to tell you about what has happened in detail about solar and wind. I just want to leave with you, in the best sites around the world, what is levelized cost of energy, which includes the land use, includes the capital investment, includes the maintenance, average over the lifetime of a wind turbine or the lifetime of a solar utility plant, is below 2 cents a kilowatt hour of generation and profit costs. The best places in the world are in the Middle East for solar, and there's very, very good wind in other places, in the United States, actually, from North Dakota to Texas. And the costs are expected to decline in the very good places to less than 1 cent a kilowatt hour wholesale, or 1.5 cents. But that's the good news. But the bad news is if you're 10 or 20% renewable, it doesn't really matter. It's a little add-on. Suppose you're 50% renewable or 80% renewable. Then the cost of renewable is not just this levelized cost, but the fact that you need other things. You need backup generation. You need a much better energy transmission and distribution system, and you need energy storage. So the real cost of renewables when you're at 50, 60, 70% has to include all this. So the levelized cost has got to be half, roughly. And there's some hope that it's going to get there, so that's good news. The bad news is I don't think the United States will ever be 100% renewables because we have an energy storage problem. And so, I don't want to debate whether it's 10%, 20, 30%, or 40%, where you need to turn on a power switch. Because let me tell you about PG&E when they blacked out 1 million people. They were really irked. But that was for forest fires. If you start blacking out people for climate change, they're going to get a lot madder. And so you need to turn on the energy, and also for industry. All right, so let's talk about energy storage. And here's a picture of my favorite battery. It's 200-year-old technology. When the wind blows, you pump water. And once you've used the energy and once it's up there, you're okay. You want water, you open a valve. That costs no energy. And so it turns out gravity is the cheapest battery if you have an existing dam. And it's called pumped storage. And so when we have batteries, the cost of batteries for half-day thing is going to be a real possibility, and even 1 day. But if you're going to use a battery once a month, then the cost of the battery has to go way down from using it once a day. Because you only get to charge once a month. Okay, so energy storage is really serious, and it's very important. And so pump storage, this is the pump storage in the world 2014. Believe it or not, Japan led the world, followed by the United States, followed by China. But by 2020, a year from today, China will lead the world in pump storage. They have very good hydropower in southwestern China. And their plans are by 2090, they will be much more than the total rest of the world combined. These are existing dams, and you have a 5% pool down there, and you just pump it up and down. The round-trip efficiency of pumping water up the hill with friction and pumping down with the same turbine is about 85% efficient if you have, a 150-foot dam. It's better than a flow battery. So pump storage is really very good. And an existing dam is very inexpensive. If you have to make a new dam, it's expensive, but people these days don't want hydro dams. Okay, so let me tell you about what's happening with electric vehicles. This is a projection of where electric vehicles will be. It's about 2% of the market today of new car sales. And by 2040, it's projected that personal vehicles and light-duty vehicles will be a majority of the new sales. That's the good news. The bad news is that means 45% of new light-duty vehicles will be internal combustion engines, and they have a lifetime of roughly 15 years. So it'll be a long time before we're electric vehicles. Now, electric vehicles today cost more than conventional vehicles, significantly more. And they, their batteries aren't good enough. There's some issues there, but I'll talk a little bit about that. But before, I want to talk about a transition a century ago from horse-drawn carriages to automobiles. And this is a picture of New York City, Easter morning, 1900 Fifth Avenue, the Easter parade. There's one automobile. This is Easter morning, 1913 Fifth Avenue. There's one automobile here, there's one horse here. Okay, this is really fast. If you think about what it required to go from horse-drawn carriages to, it's a total transition of infrastructure. It required an oil gasoline supply chain, it required better roads, it required repair shops, it required everything. So why did it go so fast? And it was accelerated in major cities in the United States because of a pollution problem. And the pollution problem was very simple. In New York City in 1880, there were 160,000 horses, and they were producing 3 to 4 million pounds of horse poop a day. It was piling up everywhere. And you couldn't deny it. And in fact, it was kind of ankle deep. And so you would have to kind of wade through the horse poop. And along came a cleaner solution, okay, which was the automobile, no horse poop, poopless carriage. And so, so let's fast forward to a century, and this is Beijing in a bad air day. It's very polluted. And there's an issue having to do with small particulate matter. Particles less than 2.5 microns in diameter is especially deadly. And larger epidemiology studies are revealing that it is really bad. In this article, they followed 300,000 people over 12.8 years, not in China because the records in China weren't good enough, so it was a retroactive study of Great Britain when they were burning coal and had a lot of PM2.5. And there's a risk factor for every 5 micrograms per cubic meter of this stuff. There's an 18% higher chance of getting lung cancer. China in 2016 was 76 micrograms per cubic meter, averaged around the whole season. Delhi is about 400. And remember, if you do math at the low numbers, if it's 5 micrograms, so it's 1.18 to the nth power. But of course, that's not true because not everybody, you can smoke 3 packs of cigarettes a day, and there's a fraction of the population that will get lung cancer. Now, it's not lung cancer that kills most of the people from cigarette smoking. It's coronary disease, stroke. Lung cancer is only third, followed by COPD. And that's also the projection of what happens in PM2.5 for a very simple reason. They're the same particle size, and they have some of the same carcinogens and other stuff. And you don't die from your first package of cigarettes or your first year of smoking. It takes 40, 50 years to build up all this stuff. All right. 10 micrograms per cubic meter is the World Health Organization guideline for clean air, but that's 36% higher chance of getting lung cancer. And so now the big debate is it's going to cost a lot of money to lower it, and you probably don't consider 36% higher chance of getting lung cancer clean air. Okay, so there's other issues going on. What's driving China? They cannot enforce a clean fuel standard. They can't enforce catalytic converters. There are technologies emerging for PM2.5 filtering. In fact, a colleague and I have discovered one of those, and for the first time in my life, I was willing to say, okay, I'll be part of a startup company, because I didn't want to be bothered by making money. I was raised incorrectly by my parents. But I thought if I could help accelerate the technology, get it out in the marketplace, it would be a good thing. So this is going on, and so there's an expectation. China's already outlawed 2- and 3-wheelers in cities. It has to be electric. Their expectation is they will outlaw in cities internal combustion engine cars maybe by 2040, but there's no way they can enforce inspections and not have people buy their way out of them. It's also true in India. It's also true in Pakistan. It's also true in many places. In fact, in California, for the first 15 years of catalytic converters, if you flunked the smog test, you went to the inspection station that would pass you. You'd have to pay twice as much, but it was okay. And it finally was known that that was happening. And so even relatively law-abiding US citizens took a decade or two. And the leaders in those other countries know it's hopeless. All right, let's talk more about batteries. So each way is a professor in material science department and engineering. He's one of our stars. We have a few star battery researchers. I started collaborating with him on batteries since I came back. And I'm focused in my work with him on lithium metal sulfur batteries because if you have any battery made from even 2 or 3% cobalt, when you go to 50% electric vehicles, the price of cobalt will go through the roof, followed by manganese, followed by nickel. Sulfur is nearly free. And so if you really want to plan for success, you've got to have something that goes to scale, and that's sulfur or some other substitute, and lithium metal. Lithium metal, you say, well, isn't that precious and rare? And the answer is not really. Lithium in the Earth's crust is about as abundant as nitrogen and chlorine. It's just how do you get it out? By the way, the charging rate, the energy density you want to double at least, so that it weighs, instead of 1,200 pounds for a full-size Tesla, it's 600 pounds, 400 pounds, means you need less battery. The charging rate's very important. If you can charge in 5 or 10 minutes, 60% charge, and it has 300-mile range, so you put 150 miles in 5 or 10 minutes, 5 minutes is perfectly okay. It's not too different. If you have to wait an hour, it's a real issue. And it's really a matter of when, not if. I'm on the board of a battery company that he founded, and we're shipping batteries at twice the energy density, but they're high cost. And there's a big push to get 4 times higher charging rates. The Tesla fast charge is 140 kilowatts. The specs of the automobile manufacturers is they want 400 to 500 kilowatts. Okay, and you can charge every other day, so it doesn't kill the battery. So this is going to come along. Again, I don't know whether it's going to be commercialized in 5 years or 10 years. It takes at least 5 years because of the safety issues that you have to put it through the paces. Lithium, this is something that's been sitting on my desk now for a long time. It's embarrassing. This is a co-directed student, Chung Lu, who's now at the University of Chicago as a professor. And seawater has very low concentration of lithium, and the molar concentration of lithium sodium is 1 in 2,000. And we figured out how to get lithium from seawater. It turns out that the major source of lithium is very, very salty lakes that then they evaporate to get them super salty, and they use chemical methods to extract lithium by precipitation. That's the major source of lithium, and it turns out, I don't know if you know this, when you drill for oil and you're lucky, you get oil, you get gas, sometimes not, and you get a lot of water. And in many places in the world, including the United States, the production of water to oil could be 10 to 1 water. And the water is not good water. So you have to process and pump it back into the ground. You can't give it to, it's mining water, it's really bad stuff, and you can't give it to sewage treatment plants. And it turns out the lithium in this water is actually, on a kilogram per kilogram basis, more valuable than the oil. So I advised Royal Dutch Shell, and I said, the joke will be in 80 years, You go looking for water, you find some oil, you pump that back in the ground, you take out the lithium. Okay, because lithium costs about $15 per kilogram. And oil market value is like, $60 a barrel. There's a lot of kilograms in 55 gallons. So anyway, so that problem is at least solved for the next 2,000 years. There's a human side to revolutions, agriculture, industrial, and information. When we went to mechanized farming, which is based on fossil fuel, diesel, you can have much more efficient farms, and the number of farmers is, you don't need the number of farmers. And so the US has 2% of the population is related to farming, but we not only feed the United States, we feed a large fraction of the world. China had 300 million, one United States worth of farmers displaced in the last 15 years, and they're expecting another one United States worth of population to be displaced. Okay, and so that's 2 United States worth of population, and where are they going to get jobs? They flock into cities. There's, you're not allowed to go to Shanghai and Beijing unless you get, it's almost like a green card. But these are issues. And automation and information technology is also creating jobs, but they're displacing older ones. And the skill set may not be the same. If you go to electric vehicles, the maintenance expected in electric vehicles is virtually nil compared to an internal combustion engine car. Most of the oil industry makes its money from repairs, not from the selling of the car. And so all those repair shops and the jobs in repair shops go away. And so that's another issue that one has to consider. Just as if you decrease the amount of use of fossil fuel, coal, oil, natural gas, those jobs go away as well. New jobs are created, but they're different jobs. So one has to be very sensitive to this stuff. But let's go back and talk about clean electricity, 1.5 cents a kilowatt hour. What will that allow? And I refer you to a very recent science article, review article written this September 2019 about renewable, it's not a review, it's a thing about renewable bonds. And on this diagram on the right-hand side, there's electricity costs in cents per kilowatt hour, and there's the energy conversion efficiency on the y-axis. And if electricity is 4 or 5 cents a kilowatt hour, there's really no way you're going to make hydrogen from electricity. It's out of reach. Because the efficiencies are not going to be 90%. They're going to be down in here somewhere. And there's also capital expenses. So you get to profitability when the electricity is 1.5, 2 cents a kilowatt hour. All of a sudden, the energy costs are a fraction of the costs of making hydrogen. And so this is very real. And what's good about this is the cost of making hydrogen is going down, and there's new research ideas as well. Beyond hydrogen, if you look at other chemicals that you can make, we now make them from oil. Most of the chemicals, virtually all the chemicals and plastics we make are from oil and natural gas. And the building block of all those plastics are ethylene, C2H4. And it comes from the feedstock is oil and natural gas. And if you replace ethylene with renewable energy, you've just reduced the amount of carbon emissions per year by about 1 gigaton. And the money is also significant. This is 250, that's 200 billion dollars a year. Okay? And so the question is, can you have thermal processes replaced with clean electricity? The answer is we don't know, but it's a very real possibility, and the oil companies are very interested in that because they know that in 50 years they cannot be in the oil and gas business. Okay? And BASF, I just came from an energy review of German Helmholtz Energy program. And BASF knows that they too have to, that's a big German chemical and plastic company, they got to be out of carbon fossil fuel feedstock. Okay, so let me tell you one little idea that, that we're exploring that has some promise. This is electrolysis in water. You plunk down 2 electrodes and you have in this, and you have hydrogen gas coming out one side, oxygen the other. If you're interested in the chemical reactions, one side, for example, in an acidic environment, those protons mean you're an acid. You go from water to oxygen plus protons. The protons migrate to the other side and combine with electrons supplied by the electrical supply, and you make hydrogen. So let's make a cartoon of what happens. This is a catalyst, and the oxygen, both the oxygen and the hydrogen are very low solubility. So the molecules look around, they find each other and form a bubble. Here's a little bubble. It's a nano bubble. There's huge surface tension on the collapse, so it creates a resistance to formation. And then the bubble grows, and when the bubble grows really big, there's no longer a surface tension issue, but something else happens. It blocks other catalytic sites. So the moral of the story are bubbles are bad for electrochemistry. And so another co-directed, this is now a graduate student, not a postdoc, with Yi and I are working on something that gets its inspiration from lungs. In lungs, you breathe in air. The oxygen passes through a membrane and transfers the oxygen to the blood, the hemoglobin in the blood, the red blood cells. It gets transported. You're burning energy. The byproducts of energy conversion are similar. They include CO2 and water. And then another enzyme takes the CO2 and it exchanges with the air. And so the secret was the membrane. If we make a very cheap polymer membrane that doesn't like water, what you can have is you can have the catalyst on this side, and then the oxygen molecule, the hydrogen molecule, looks around and says, ooh, I don't want to be like a bubble. I'd rather escape because of the diffusion constant in gas is 10,000 times faster. So this is showing promise. It makes much better, it's catalyst agnostic, so the rates are much higher, et cetera, et cetera, et cetera. So the answer to what we're trying to do is if you have clean energy, you reverse the combustion process, CO2, H2O, turn into hydrogen, other things, liquid hydrocarbons. Why? Liquid hydrocarbons is fuel, but it's also very important. A quiz, how much does it cost to ship crude oil halfway around the world and store it? On a per gallon basis, the answer is 2 cents a gallon. Transcontinental shipping and supertankers is nearly free. That's why we're shipping all sorts of stuff all around the world now. And so think of an oil tanker as an intercontinental transmission line. Okay, now I'm way past my time. I just want to, then one thing, if you're going to talk about sustainability, you cannot have a world that's population is increasing. But every economy in the world is based on having more young workers support a smaller aging population. That's known as a pyramid scheme, where early investors sell more shares to older investors and you pay off the early investors. It's also known as a Ponzi scheme. It's a slow pyramid Ponzi scheme. As long as you have more younger workers, you can have a pretty inefficient thing. And so here's the thing. So what's happening naturally, and this is, if you don't know this is called Gapminder. It's wonderful. You can plug in what parameters you want on the y-axis and the x-axis. So I plug in fertility rate babies per woman. 2.1 is break even. This is the fertility rate in India. It's about 2.2. This is income on this side. You can also put in education of women. You can put in all sorts of stuff. And even India is going to neutral population growth. Mexico is at neutral, Germany is below. Every country is this way, except Africa. So Australia and New Zealand, well, there's only, some sheep and things like that. But North America, Europe, Eastern Asia, Southern Asia, they're all expected by 2100 to be negative growth. And the only wild card is sub-Saharan Africa, which is expected to grow from 1 billion to maybe 4 billion. And so if you look at the same thing with sub-Saharan Africa, I plotted Uganda, Kenya, Nigeria, and South Africa. These straight lines mean there were no wreckers, and the birth rate here is 8.7 per woman. Very, very high. South Africa is now going here. These slotted figures are the rest of the world. So you get richer, you get more educated women, it goes down. But Africa is also going down. Perhaps not fast enough. If you go to Africa, you find that in many places in Africa and South Asia, it's human power that transports goods. Water, you don't have energy, there's no energy for irrigation, there's all sorts of issues. This picture on the lower right-hand side is what I saw a lot of when I was there, 200 pounds worth of potatoes being pushed by a bicycle because you can't afford fuel. So that's what's happening. There's no irrigation, there's no thing. So it's as though the Industrial Revolution has not occurred. The productivity in these areas is very poor per hectare of land. On this axis is fertilizer, and this axis is crop yield. This is the United States. This is Nigeria and Africa. This is on a log curve, so we're looking at factors of 100 times more fertilizer and 20 times more yield per acre. Okay? But it requires energy. All right, so in addition to that, those are other population curves. We also need another measure of wealth. The current measure is GDP, which means you produce more stuff, like cars. And so if you have more cars, you increase the GDP of a country. It means you promote consumption. And that is not a good thing. There's a human development index that is GDP per person on a log scale plus longevity plus level of education that says this is a better form of real wealth. We need something a little better than that because longevity, as medical science advances and we make good inroads on cancer, heart disease, stroke, we're left with so far a disease we have not made any inroad in that forms of dementia. And so and by the time you're in your mid-80s, half the population will have early signs of Alzheimer's by the 90s. Whether it's really clinically diagnosed or not. And so we need to do something here too. But this is, so you've got to recognize we're living in a Ponzi scheme and we have the wrong incentives. Because all the politicians want to brag about increased GDP. What you really want is a better life. And you and I know that if you're commuting an hour and a half each way, this is not a good life, okay, as an example. And so, again, these metrics actually mean something, and so we need a rethinking of this. So let me end by telling you about one of my favorite pictures. It was the first Apollo mission that orbited the moon. The last of the 4 orbits, they turned the capsule towards Earth, and they actually had handheld cameras, and they started taking pictures. And the astronaut who took this picture, now called Earthrise, and it's oriented in the right way because, we're going like this, and never mind. And so Bill Anders, the astronaut who took this picture, said, we came all this way to explore the moon. The most important thing is we discovered the Earth. Now, look at this picture. It's not rocket science. The moon is not a good place to live. No water, no air, no magnetic field to shield you from radiation, cosmic rays from the sun, so if you don't die of lack of water and lack of air, you will certainly die of cancer. From this vantage point, this is a pretty good home. It's even better if you get closer and look around. Black, nothing else. So since 1968, we found that we are altering the climate of the Earth, it's humans, and there is really nowhere else to go. Don't think of going to Mars. For exploration, yes. Living there, no, it's not going to work. Also, Mars has no magnetic field also. They used to have one. So you also have lethal doses of radiation, but you'll get a lethal dose on your way there. So as this is our home, it's our only home, and we better take care of it. Thank you.
I think we'll have just a few minutes for questions. I don't know, can we bring up the house lights a little bit here? Thank you. I'll let you go ahead. And let's see. There we go.
Okay.
Why don't we,
So sorry to go so long. I got carried away.
I'll let you. David?
So you showed us heading up above this threshold. So I thought you were maybe going to then talk at some point about carbon capture technologies or ways to get us down below.
Okay. So the question is, we see blowing past 2-degree guidelines. I think we may go past 3. We don't know, well, let's start with parts per million carbon dioxide, because the climate models are big uncertainties of what happens. We're going to go past 550. Forget about 450. We're at 410 now. We'll probably go above 600. And so the question is, if we do that, and we've got carbon dioxide in the air, and its mean lifetime is 10,000 years or 5,000 years, what do you do about it? And so the answer is you do need to capture carbon from the atmosphere. The best way to capture carbon are plants, agricultural plants. Plants we now plant capture twice as much carbon dioxide as all greenhouse gas emissions. If you can take those plants, extract the food from it, get some chemical value out of it, and then store the rest underground, you have a very good carbon capture mechanism. I think may be much cheaper than direct air capture. But we will definitely need some sort of carbon capture. But the first order of business is capture carbon from the, you can clean up the ocean and the lakes, but it's easier to not stick it in the ocean and the lakes. And so you need both. So carbon capture is an essential part of this solution, because we're going to go past where we want to be.
And what's the time scale at which you could plausibly actually reduce the amount of carbon?
It depends on the technology. So right now we don't have a mechanism. Direct air captures $200 or $300 a ton. There's no price in carbon, so why would you ever do that? So the first plausible thing is if you can take agricultural residues, wheat straw, corn straw, rice straw, create a chemical of value, and in the process help pay for that, that will do it. That will help do it, because you need the economic incentive. Now, in the end, you're going to need a price on carbon. The estimates on how much price you need vary, but a person Bill Nordhaus, who got a Nobel Prize for his economic analysis of carbon emissions and how much it would cost, he got in 2014, he estimated that the low-cost option is 650 parts per million and $300 a ton. It's a hard-nosed economic choice decision based on projections of technology, but not breakthroughs in technology, more Moore's law, slow, gradual projections, large uncertainty. But that's not a good answer, because that's three degrees, and we saw what happened with 1 degree. 3 degrees is not good, maybe 4. Okay, so carbon capture is necessary. What price? I don't think the world will ever go for more than $100 a ton, between you and me. Yes?
What's your opinion on the prospect of nuclear energy?
Okay, nuclear energy. So let's go back to, let me rephrase the question. you need energy on demand for some fraction of energy. And it depends on where you live in the United States. We're blessed with lots of renewable, and we're a big country, and we have transmission distribution. We have Canada, we have Mexico. I have no problem with today's energy costs going to 50% renewable. That's in the cards. I don't see how we can get to 80% renewable. Because that means the standby generation, the energy storage is too expensive right now. It's not even close for battery storage, and people won't let us build new dams. So we need a breakthrough in energy storage at utility scale, because if you want to store, how much power do we use? Power as opposed to energy. It's about a terawatt in the United States. So 1 terawatt hour, so one day is 12 terawatt hours. We have, I don't know, a couple hundred megawatts hours, except for the dams. The dams are a lot. So we need to do that. Nuclear. So then we have fossil or nuclear as something you turn on. And fossil means you capture carbon, but you're only going to capture 90%. And you've got to sequester. And people don't like pumping carbon dioxide underground near where they live. So then there's nuclear, but nuclear is too expensive. We forgot how to build nuclear power plants on budget, on time. So, but I'm for nuclear, by the way. But we have to build them on budget, on time. And the only way I can see that is you stamp them out in a central factory of small modular things and you ship them. And I was, when I was Secretary of Energy, I was supporting engineering designs of small modular reactors. But you need about 100 ores before you even think of going to any sort of production. Small modulars can be inherently safe. You lose power, access to power, water, everything, and you can make them with enough heat inertia that they will not melt down. So the safety issue essentially goes away, and you can put them underground.
Do you think we'll ever have fusion reactors?
I don't know. The biggest hurdle I see, I have faith in ITER and other research that they will solve the plasma problems. But the biggest issue with fusion, as with nuclear, is the capital X investment. The estimated capital X investment is a wild card. We have no idea in fusion, but a nuclear reactor now costs $10 billion per gigawatt. And most utility companies will not risk $10 billion, because if you're 3 years late in paying interest on $10 billion, you've made a financial hole you can never come out of. And so if you have, and so the first N reactors will have to be supported by an international consortium of governments. But if it's $20 billion, it's still too big a risk. But we don't have any idea what it will really cost, because we don't even have, it's a science experiment at the moment. I have a joke about fusion, if you don't mind. There's a fusion scientist, and he works all his life in fusion, and they say, will this ever become commercially viable? And he says, not in my lifetime, but if we can get it, it's so important that it would be great for the world. So I might spend my entire career working on fusion. Old things come to an end, he dies, he goes to heaven, he goes to St. Peter and says, I need to ask God a very important question. And St. Peter says, this is not only not done, but you are such a good person on earth, we'll allow this. So he goes before God and says, God, will fusion ever become commercially viable? There's a long pause, and God says, maybe so, but not in my lifetime. Don't hold your breath. And then I was just in his interview review, and there's Bernard Bigot, who's a longtime friend of mine. He's a nuclear guy, and he took on ITER, and it's finally on track. It slipped 20 years, and he's a good guy. And he was saying, yeah, and everybody's saying, when is fusion going to come? Mañana. It's, first 20 years, it was 30 years ahead, and now it's 50 years, and so that's progress, because now it's only 50 years ahead, but every decade advances by, it's still 50 years ahead. So I had another joke. I said, this mañana, So the Spaniard asked the Italian, do you have a word like mañana in Italian? And the Italian says, yes, but it doesn't convey the same sense of urgency. Sorry. Yes? So the question is, do I know when the world will end because of global warming? And the good news is the world won't end. Humans won't go away. Polar bears won't even go away. They survived other warm periods. There will be huge social disruption, and some fraction of the population could die. The bad news is we have historical records of what the world was like at the present carbon concentration, and that goes back not a million years, but it goes back 3 million years. And it was different. Insects were this big. and so life will go on, but social chaos might reign. There's all sorts of things that might happen. The world will not end. Your life might not be so hot because of social unrest. Because the United States is not going to be immune by being insulated by 2 oceans. And that's something that the American public has to understand. You know, it's not a Europe problem. It's a world problem. When I was Secretary of Energy, India was deathly afraid that climate change would, most of Bangladesh, 140 million people, very low-lying, they're very poor, they would migrate over to India. And India said, what are we going to do when these people, tens of millions of people come over? We can't shoot them at the border, which is true. And they're doing what Trump is trying to do. They're trying to build walls, but they're leaking over. And so these are very poor, predominantly Muslim people going into predominantly non-Muslim country, and it's an India problem, as well as a Bangladesh problem. And so this is serious business, and it's happening because the sea level is rising and they're leaking over. Yes?
How about the Green New Deal?
Green New Deal, it's more of an aspiration. I'm all for aspiration, but I'm also a technologist. I want science and engineers who invent stuff that makes it so cheap that it takes less political will. You will need some political will, but when I hear we have all the technology, we just need political will, it's only a matter of money, and it is true, energy is all about money. And most of the world public will not want to double energy rates. And so it's very sensitive politically. And so that's why I talked about, you know, there's an old saying I quote a lot, is there's a former Saudi minister called Sheikh Yamani, and he said the Stone Age did not come to an end for lack of stones, and the oil age will not come to an end for lack of oil. And there's great wisdom in that. He's a former Saudi oil minister. That's not why he's the former Saudi oil minister. What he meant was, when you transition from stones to metal age, you don't look at the stones in the ground and say, if it weren't for some liberal politicians, we wouldn't have these stranded assets. Right? Not every stone has to be something. And so suppose you get $2,000 electric vehicles, fills up half in 5 minutes, full 80% in 20 minutes, you would buy an electric vehicle because there's no maintenance, okay? And the operation costs plummet, and you don't have to wait, and you don't have to put an expensive charging thing in your garage, or you have to have an employer. And so all those things go away. And so that's why you have to work on fast charging batteries, as well as cheap materials. The cost of materials in today's Teslas are 30% of the cost of the battery, just the materials. Not the manufacturing, it's the materials. And this is 2%. If it's 50%, it's untenable. So that actually, if you're young people out there, if you focus on work on the right problem, Don't work on little incremental stuff. And so you need faster charging batteries, you need batteries with abundant cheap materials, you need other stuff, you need all sorts of things. But we're going to get there. But it's being slowed up a lot by incumbent industries. Incumbent industries have jobs, and when you have jobs, you have to think of replacements for jobs. That's a reality. Yes?
Do you think there's a type of technologies like wants and needs, like some technologies that we would need because we need it as humans, and there are some technologies that like wants, we want it because things are much easier? And do you think as humans we would really go after our wants? Or
Yeah, so the question is, there are wants and there are needs, and there's an old Mahatma Gandhi say that. The world has enough resources to satisfy all the people's needs, but not every people's wants.
so even like in the past, I think everyone lives without technology and it's like
Between you and me, I don't want to do, I don't have air conditioning in California because we do thermal management. We have a house in Palo Alto, it gets to be 100, 5 times a year, but it's cool at night, so you cool the house down, and then you put shades, very reflected shades in the south and west facing side, and so even if it's 100 outside, it's 75 inside. But, no people are willing to do that, and it's a well-insulated house and things like that. But if I was living in Hong Kong or in India, I would want air conditioning. So is that a want or a need? Well, it's like getting 500 megabytes per second. You never will go back to 5. And the want became a need very quickly. Remember, you're too young. Remember the days of DSL and kilobytes per second? And so it's hard to separate wants and needs. Do we really need to eat a couple pounds of steak a week? No, there's old habits, and so you can't force people not to eat steak, but you can get a younger generation to say, hey, you can develop new taste habits. But that's a want, because you feel good about not eating as much meat. And so there's also, it's complicated. You can't legislate this. But anyway, maybe a few more. Yes?
Is there a value in, or how much of a value is there in recycling compost?
Oh, how much value is there in recycling? These are all great questions, by the way. A lot of recycling makes you feel good, but it sometimes may or may not be material. And now what's happening is there's so bad pollution of plastic that you want biodegradable plastic. But biodegradable plastic is terrible because it means you take fossil fuel out of the ground, it biodegradable goes right into the atmosphere in methane or CO2. What you want really is to not throw plastic into rivers and oceans. You don't want biodegradable. But there's a huge, the petroleum companies are trying to make it all biodegradable or recyclable because there's such an appalling stuff about, finding plastics in fish and whales and things, but it's worse than that because now there's unknown things about microplastics and nanoplastics that show up in people's blood, and what's the long-term effect. What you really want is to dig up, if you want to use fossil fuel, a dream would be turn natural gas into hydrogen and you get carbon, and turn the carbon into structural material that replaces concrete or steel. And it's non-biodegradable, and it doesn't, so nothing goes into the atmosphere. Okay? Concrete is 8% of CO2 emissions in the world, going to 10%, just concrete. Concrete, steel, and plastics is 25%. Maybe 20%, 20 to 25%. So it's very significant what to do about this stuff. Yes?
What's something you're excited about that's coming about? Something that
Electrochemistry, Batteries, I'm working on batteries. That's, I think, going to be a reality. Electrochemistry is going to be a reality. New technologies in transmission distribution to balance the grid to where your 50, 60% will happen. Again, there's also money involved, and the incumbents want to stay in business, and so there are issues here about that. And so you want to make these transitions. You want to be sensitive to people whose jobs are going to be displaced. That's very real. And so it's not just strictly science and technology. You can't be tone deaf to the fact that, 2 United States population worth of Chinese farmers are homeless.
Okay, I think we got to maybe cut off the questions at this point. I want to do one more thing before we leave for the evening. I want to present you with a plaque that commemorates your lecture today. And the nice thing about this plaque is that it has all 56 names of the previous speakers, and I think as you have a moment to go through those, you'll recognize a few names.
I recognize most of the names, and then my only question is, how come it took you so long to invite me?
Let's thank the speaker one more time.
You want to tilt it,